Okay, let's start. Okay, so this is the first class of choose a holiday. So we have very early choose a holiday in this semester. Did you have a good holidays? Good. Okay, for some of the holidays is a good time for enjoying gathering with the relatives. But some for some of the holidays not good because well, you're a student and then you have you don't need to achieve some good you don't need to have good achievements not yet. So I think it's good. So and but you have potential for your future. So and then so actually because of your potential, everyone think that you you have a bright future, right? But your future is determined by the current, your potential, and then your current effort. So this is the very old problem. But it looks like it's outdated problem, but it's true for your life. So if you so based on your potential, and then if you have good effort, then you can get better future in your life. Okay. So yeah, so I know that it's kind of outdated problem, but it's true, right? Okay, so because so before starting today's class, I will introduce about the homework assignment. So I'll start with the outdated problem. Okay, so as I announced in the first class, we have 5 homework assignments, and we have 4 lab assignments. And then also, if you read the syllabus of this course, and you can find that brief content, the brief plan of the homework assignment and the lab assignment. So actually, in the homework assignment, we have several questions that ask about what you learn in each chapter. Okay, and then before midterm we have 3 homework assignments, homework 1, 2, 3. Okay, and then after the midterm, so we have 2 homework, homework 4 and homework 5. So it means until our midterm will cover until homework assignment number 3, homework 1 to 3. And then our final will cover homework 4 and 5. Okay. So we have 4 lab assignment. And then so even though this is the tentative schedule for this course, but I try to make a schedule as I announced in this slide. So which means that homework 1 will be out in week 2, right? So we are actually the last day of the week 2, but maybe tomorrow is the last day of the week 2, right? It's September 14th. So which means that the homework 1 will be out. So, and then actually I already posted the homework 1 on the blackboard, and then it will be revealed to students at 10:30. Okay, so I believe you can find homework assignment number 1 on the blackboard. Also the homework policy. So actually I need to explain about the late submission policy. So usually the submission deadline is at the end of the day. So it means that it's 11:59 p.m. So it's the end of the day, and then the 20% penalty is applied for every 24 hours, right? So which means so this is the deadline. It's 11:59. So and then after that, your score will be 20% reduced. You will get 20% to reduce the score of of your original score. So if this is the example, so you will get 80 points if your original score is 100 points, and then you submit 20 or 12 hours later. So this in the with it's the so your submission is delayed for 12 hours. So 20% of penalty is applied. Okay, and then so after 2 days, we will not accept the late submission, which means that you will get 0 point if you submit your homework assignment or lab assignment after 2 days of the wrong deadline. Okay, so this is the homework late submission policy. Okay, any question? And then, so actually, I posted the homework 0 and the homework 1 on the Blackboard. Actually, the homework 0 is just for surveys. Okay, so in order to check your current status for this course, I asked some questions on homework number 0. Which is just and as you can see, the score is 0 point. The 0 point will be assigned, so you can submit your homework 0. And then if you want, you don't need to submit the homework number 0. It's just for surveys. So let's see the homework assignment here. You can find the instruction. I don't know why. So as you can see, you can find the homework 0 here on the Blackboard, and then I assign the 7 questions. It's simple questions, but it just the question just ask your current status for this course. Okay. Okay, and then I believe the homework 1 is already posted and then released to you. So this is the example of the homework problems. Okay, so homework questions as what you learned in this course. Actually, after every chapter, I will assign homework assignment for students. Okay. Okay, so and then you can submit your homework results, the homework answers via Blackboard. So we will accept the PDF format only. So just to generate the PDF format for your homework answers, and then submit your homework answers on the Blackboard. Okay. Okay. Any questions? Okay. And then it's very important. So you need to answer your homework questions by yourself. So actually, it's very important. So I repeatedly said that. So actually, until the last semester, I said that if you can solve homework questions by yourself, I believe you can solve midterm or final questions easily. So I believe the difficulty level of the homework assignment is similar to the difficulty level of midterm or final exams. Okay, so it's very important. Right? Figure out homework question by yourself. Okay, and then if you have any questions, you can post your question on the Blackboard. And then if you want to get help from me or PAs, then you can send email or make an appointment, and then you can visit my office, or you can also stop by our PA's office. Okay. So please make use of Piazza 2. So please make use of your instructor lead and then PA. Okay. And then, so before, also before starting today's class, we will take a pub quiz. So actually, in this semester, I changed the pub quiz logistics. So actually, you can connect to your Blackboard. Okay. So now you can find that, oh, this is the quiz number 1. Okay. Got it? Then also you can use your smartphone for connecting Blackboard. Okay. So please take your quiz, the pub quiz right now. Okay. So this is quiz 1, and then just connect the Blackboard using your tablets, laptop computers, or your smartphone. So you can use also your smartphone. It's very easy. Actually the quiz questions are very simple, and then also the answers are, which means that the answers are also very easy and simple. So you can click the quiz number 1 like here, and then you can begin the question like this. Oh, so actually it's very small, the fonts so actually on my computer, the font size is very small. So you can find the question number 1, 2, 3, 4 here. And then also you can submit your question, your answers here using this sorry, very small. Okay. So please take the hard case right now. So showing I will. So this is the currently it is 10:42. So I will start today's class at 10:46. You can take this copy until by 10:46. And then so if you complete your copies, then you can submit your answer, save, and just click the save and submit for it. This is the test that you can for your live mode, or you can look for any it's just a piece for your running. Okay. Okay, I will close the quiz, the blackboard. Okay. So it's 10:46, and then I will close the quiz one. Oh. Okay, quiz is not available right now, so then I will explain. So actually, as I said, so I assigned the quiz for your learning. So actually for reviewing what we learned in the previous classes. Also, so I sometimes use the quiz for checking your attendance, real attendance. So even though this is the this course use the self attendance check system, so you can check your attendance using Blackboard, right? So sometimes I will check your real attendance using the quiz. Okay. Okay. So let's see the quiz questions. So we have actually 4 questions here. The first question is that write the performance metrics frame. So we learned 2 performance metrics in the previous class, right? So what is this one? Time gap between the start time and the end time of a task. This performance metric is called response time, right? So this is the response time. And then sometimes this metric is called the latency. Okay, actually the latency. So we frequently use the latency instead of response time. And how about the second metric, amount of work done within a unit time? So we just measure the amount of work already done during some time, some period. It's throughput, right? It's throughput. So actually, these 2 metrics are very important for measuring the performance of a computer system. Okay, and then as I said, so we just focus on the latency because we focus on the performance of a single application or single thread. It's called a thread in the computer system. So we just focus on the latency. So and then so we measure the execution time of one application. So actually we measure the CPU time of a single application for measuring latency or response time. Okay. So why do we use CPU time? Because the computers are very complex system. Actually, our application is executed on operating systems. So when our application is executed, then operating system overhead is included, also the many other overheads such as the I/O time or the network time, network delay is also included in the total execution time. So in order to compare the performance of a processor fairly, we just reduce. So we just remove these overhead, and then we just measure the pure execution time on CPU, the processor. So we just measure the CPU time. So how can we calculate the execution time? So in this, so it's very important. So I said that you need to remember this equation, how to measure the execution time of an application. So in this problem, so I provide the instruction count, CPI, and then clock frequency, right? So actually, the execution time is instruction count multiplied by CPI multiplied by clock period. Okay, And then actually in this question, I provide clock frequency. So you know the clock frequency is the F is the 1 over TC clock period. So actually in this example, TC can be 1 over F, so the inverse of a frequency. So you can just use this information. So 50, it's a billion, 10 to 9, 1.6, and then clock frequency is 2 gigahertz. So clock period is 0.5, right? 10 to minus 9. So actually, you can easily calculate them. You can calculate, right? 50 multiplied by 0, it's a 40, right? It's a 40 seconds. Okay. And then the third question asks the average CPI. So in this example, so in this question, I assume that the application includes the two instructions, instruction A and instruction B. And the number of instruction A is the 20 million, and then CPI of instruction A is the 3. Then it's a 40 million, and then CPI of the instruction B is the 1.5. But then how can we calculate the average CPI? Okay. So if you remember the definition of a CPI, what is the CPI? It's a clock per instruction. So in order to calculate the CPI, we need the information of clock counts. So we need number of instructions, right? We can easily calculate the number of total instructions. You can just add the number of instruction A and number of instruction B. It's 6 million and clock count. Using the CPI information of instruction A and then number of instructions of number of instruction A, then we can calculate the clock count for instruction A, right? So it's 20 million multiplied by 3 plus, and then for the instruction B is the 40 million multiplied by 1.5. So we can calculate the CPI like this, right? So this is the clock count by instruction A. By multiplying number of instruction and CPI of instruction A, we can calculate the clock count for instruction A. Okay, and then also for the instruction B is the same. So by multiplying number of instructions and then CPI of the instruction B, we can calculate the clock counts for instruction B. You can just add the total number of instructions is 60 million. You can calculate the average CPI easily. Okay, so this is the example. So in the previous, okay. Okay, so in the previous class, we learned about how to measure the performance of a computer system. Okay, so it's very important because not to actually everyone wants good computer system, and then as I said, good computer system, good computer systems mean best computer system. Okay, and with the computer system that can run with a lower cost, and then cost includes the manufacturing cost and then running cost. Because the computer is, so we need electric power for running computer systems, so which means that we need to reduce energy consumption of the system. Okay, low cost and then high performance is very important. So in order to measure the performance, we use the response time, and then we can actually, the performance is the inverse of execution time. It's very important. And then we use the metric performance comparison like this. Okay. And then, so this is the very important equation. Now to measure the CPU time, we just use the instruction count multiplied by CPI multiplied by clock period. So why? By using this equation, we can focus on, we can figure out which part need to be improved by using this equation. So, for example, if we improve the algorithm of our application, we can increase the instruction count, but then possibly CPI, because the CPI is also influenced by application, right? And then programming language also influences instruction count and CPI. So for example, if you write the same program with C, then and then if your friend write same program with Python, then the program written in C will be much faster compared to Python. Python is actually very slow, okay? Because the Python is the interpreter language, not compiled language. Also, compiler influences instruction count and CPI, ISA, instruction set architecture. So we will learn about the instruction set architecture in chapter 2. For the x86 or ARM processor or Intel processor, such as the x86 processor, so which means the instruction set architecture. So if the instruction set architecture is different, then the instruction count, CPI, also the clock period, hardware is also influenced. Okay, so this is performance summary. And then also we can use another performance metric called MIPS. So it is called MIPS, the MIPS. The MIPS represent millions of instructions per second. Okay. So which means that, as you can see, the first M means the billions. So actually, so which means the MIPS represent the number of instructions executed per second. Okay. So this just counts the number of instructions executed during a unique time. Okay. So how can we compare the performance of a computer system using MIPS? So, and then intuitively, if computer A executes more instructions compared to other computer system B, then we can say that computer A is faster than computer B. Why? Because so computer A executes more instructions. Okay. So if the instruction count is the same and then the computer executes more instructions, then which means that we can complete the same task more quickly. Okay. But in order to use MIPS for the performance metric, then we need to use some strict constraint. So which means that so we need to meet some conditions in order to use the MIPS. What is the condition? What are the conditions for we need to consider? So MIPS just mention the number of instructions per time, and then so which means that so actually the performance, the execution time is the instruction count, DPI, and then TC. So which means TC is actually we can calculate this equation like instruction count, DPI, and then frequency. So it's the frequency, the number of clock cycles per second. And then, so actually, if we, in this equation, we have the some time information using the frequency. And then if the frequency, so if the instruction count is the same, and then if the frequency is higher, then and then CPI is the same, then which means that MIPS is higher if the frequency is higher, right? So in this case, we can use MIPS for measure comparing the performance of two computer systems. Okay, using the MIPS, we can also represent also execution time. But this I assume that so not to compare the two computer systems, and then for this equation, not to use the MIPS, I assume that the instruction count of one application is the same. Why is it important? So I said that number of instruction count of one application is the same. Why? As we learn, the instruction count is influenced by algorithm. So the different algorithm. But let us assume that the algorithm is the same. So it's the same formula. But also the instruction count is influenced by programming language. Also, I see instruction count is also influenced by compiler and instruction set architecture. So, in order to use the MIPS, we assume that the instruction count is the same. But as you can see, the instruction count is affected by programming language, compiler, and ISA instruction set architecture. So in order to use MIPS for measuring the performance of a two computer system, then we assume that our application use the same ISA. Okay, so the applications need to be compiled using the same instruction set architecture. So for example, this is application A, and application A is compiled using x86 and then ARM architecture. Then the instruction count is different. So for example, the x86 is the CISC type instruction. So instruction count usually, I said usually, the instruction count is smaller if the same program is compiled using x86 compared to ARM architecture. Okay, but ARM architecture is simpler, so even though the instruction count is larger, the ARM processor can be faster. So if the instruction count is different, then we cannot use MIPS. Also, another condition is the compiler. As you can see, the instruction count is influenced by compiler option. So if you are familiar with the PCC, it's a GNU compiler, then you may know that GCC has many options, and then also GCC has many optimization options like -O and some numbers. So this -O option besides the optimization radar. So which means that if we apply the error optimization option, then the instruction count is changing. Okay. So in this case, then we cannot use the MIPS. So just remember that not use MIPS number of instructions per second, then we assume that the number of instruction count, the instruction count needs to be the same. Okay. So sometimes students are confused. But you just think that, oh, if our computers can execute more instructions, so we can say that, oh, this computer is better, but it's not true. Okay? And we need to consider some conditions in order to use MIPS. So if we see the homework questions, then you can find some questions regarding MIPS. Okay. Okay, so now let's think about the power consumption of the computer system. So until now, so we discussed about the performance, which means the latency of a computer processor. Okay, this latency is related to the performance of a computer system. So now we will discuss about the power consumption of a computer system. So as you can see, this is the power. And then why do we need to discuss about the power consumption? As I said, we also need to consider low cost. So, and then as I mentioned, we can distinguish the cost of the computer system as the manufacturing cost. So actually we need to make the CPU chip using semiconductor technology, and then we need money to make CPU chips. And then also another important cost is the running cost. So computer is the electric devices, so we need electric power to run computer systems, right? So, and then why do we need to consider power? Because the power is related to the running cost of the computer system. So, and it's very important. Why? The power consumption of a processor determines the first running cost. So let us assume that you are running many computer systems, many server computer systems, and then if the server computer systems consume much power, then you need to pay more money. That is not good. Also, think about the mobile devices. So everyone wants to use mobile devices for a longer time. But the power source of the mobile device is a battery. The battery has the limited electric charges. So if a processor consumes more power, then the running time of your mobile device will be shorter, right? So that's why the power is also very important metric for computer systems. Actually, very important. Okay, performance powers are two important metrics for computer systems. So let's see the trend of power consumption of the processor. So in this graph, you can find that x-axis represents the processor name of the Intel CPUs, and then the y-axis is the clock rate. And then another y-axis, so this is the clock rate, and then this is the power. So this y-axis represents the power consumption of a CPU, Intel CPUs. So this y-axis is the log scale axis. So as you can see, so this is the Intel CPU name. So actually, the Intel 8286 is a very old generation CPU. The clock rate, the clock frequency is just 12.5 megahertz. You cannot imagine this low value, the low clock frequency. But first, when a CPU is first invented, then clock frequency was very, very low. So which means that the CPU is very, very low. But if we just check the power consumption of the CPU, the power consumption is just 3.3 watt. It it's also very, very low. So for example, our mobile processor. So I said that our consumption is very critical for mobile processors because mobile processors use the battery. But the power consumption of typical mobile processor is around 5 watts. Then this 82, 86 is the desktop processor, so which means that this processor is not mobile processor. But power consumption is just 3.3 watt. So recently, the TDP, the power consumption of the processor is relatively high compared to the old CPU. The recently it reaches the 100 watt for Pentium 4 Prisca. Okay, so why? We can check the clock frequency. The clock frequency is increased by CPU generations because everyone wants by better CPUs, which means that high performance CPUs. And then in order to increase the performance of the CPUs, the best way is to increase the clock frequency, right? Because the key execution time is instruction count, CPI, and then 1/f clock frequency. And then if we increase the clock frequency, then we can reduce the execution time. So we can increase the performance very easily. So we discussed about the semiconductor technology, so which means that if we can reduce the size of semiconductor devices, then we can use faster device transistor. So if we use advanced semiconductor technology, then we can easily increase the frequency of a CPU, which means that we can increase the performance very easily. Okay. But as you can see in this graph, the power consumption of a processor also increases dramatically. Okay, because in the CMOS IC, the CMOS integrated circuit technology, the power consumption of this CMOS circuit is determined by this equation. Actually, this is it's a proportional, not equal. So let's see the power consumption equation. The power consumption is proportional to the capacitive load. What is the capacitive load? So actually, if we see the circuit of a transistor, then the transistor just turn on what turn off the our circuit. But when we turn on the circuit, then the electric charge is stored in the capacitor. And then using this amount of electric charges, then we determine the level of the output of the circuit. So which means that we just determine 1 and 0 using electric charges stored in capacitor. So actually the capacitive load is proportional to the size of a chip. Size or the number of transistors. So actually, if we increase the number of transistors, then also the capacitive load is also increased. And then voltage. So voltage means the supply voltage. So if we are interested in desktop computer assembly, and you can also, if you are interested in CPU overclocking, then you can know that, we can adjust supply voltage to CPU, right? So this voltage represents the supply voltage to CPU. So as you can see, this voltage, the power consumption of a CPU is proportional to the square of supply voltage and frequency, the clock frequency. So using this equation, we can know that the power consumption of a CPU is proportional to the size of a CPU chip, the capacitive load, and the square of supply voltage and running frequency. Okay. So as you can see, when the CPU generation is changing, the clock frequency is increased, but recently it is saturated because of this part. If we increase the frequency, then the power consumption is also increased. And then why it actually is related to the running cost of the processing. And then actually, so the power consumption is proportional to the cube of frequency. I will explain later. So how can we reduce the power? Okay. Yeah. So one student has said, so nowadays the CPU manufacturer does not try to increase the clock frequency. That's right. So because of the power consumption issue, then the clock frequency of a CPU is nowadays saturated. They can increase the clock frequency, but if they increase the clock frequency of the CPU, our CPU will consume very much power, like the air conditioner or even the. So sometimes someone said that so actually as you can see, the clock frequency increased exponentially. And if this trend is continued, then someone say that CPU will consume the electric power, which is similar to the power of a nuclear reactor. So it's ridiculous, right? So because of the power, we cannot increase the clock frequency of the CPU. It's a very good question. Okay, then how can we reduce the power? It's very simple. So based on this equation, so we can calculate how can we reduce the power of the CPU. So for example, in this example, the new CPU has the 85% of capacitive load. So which means that the size of the CPU chip is reduced to 85% of the old CPU. And then voltage and supply voltage, and then the frequency is also reduced. So based on this equation, and then if this information is given, then we can calculate how much power is reduced. Okay. And then also why power is very critical. And then recently why the power matters in the computer system. So what is the power wall? So actually the power decides the running cost. Also power decides the heat dissipation on CPU. So heat is also very critical. So I believe someone knows about the Samsung gate with the mobile processor, right? So actually the Samsung limited the performance of the mobile CPU when you play games, because when the mobile processor runs game applications, and the processor displays more heat. Heat is also very critical. So if the CPU consumes more power, the heat actually the temperature of the CPU is also increased, and it's also very critical for the CPU because our semiconductor can run properly on certain range of temperature. If the temperature is very high, then circuit will be broken. Okay, that's why the Samsung limit the performance of your mobile CPU is because of heat dissipation. Okay, then also another problem is that we cannot reduce voltage. So it's very actually. So I will explain about the large scale. Okay, this is the another equation of another equation to measure the dynamic power of CPU. Okay, so actually the equation is very similar to the symbolize this equation. You know, this is the dynamic power consumption, and then the dynamic power consumption is the alpha. The alpha means the activity factor because our circuit consumes dynamic power when the output level is changed from 1 to 0 or 0 to 1. Okay, so theoretically the transistor, the CMOS transistor, does not consume power if the output level is not changing. This is theoretically, but if the output level, so which means that the result of the circuit is changed, then the dynamic power is consumed. So alpha means the activity factor, and then C is the capacitive load, and then VDD is the supply voltage level, and F is the it's actually the same equation. But so I will explain about the dynamic scaling. Actually, it is also very important. Dynamic scaling means that we can reduce the size of transistor if the transistor technology is advanced. So, for example, in the previous class, I mentioned that 5 nanometer technology. So, which this number is related to the size of transistor. So, actually, this number means the width of transistor channel. Okay, so actually this number is the 1D dimension. Okay, just this number represents the width of transistor channel. So which means that if we reduce this number, then the size is also reduced. Okay. So this is the 1D dimension, and then so actually the area is the 2D dimension. So which means that if we reduce this number as the 1 over S, so S means the scaling factor, then we can reduce the size of a single transistor by 1 over S squared. Okay? Because the area is the 2D dimension. And then another benefit is that the size is reduced, so which means that the capacitive load is also reduced. So I mentioned that the capacitive load is related to the size of a chip, size of actually the entire chip. And then another benefit is the BBB. So if we reduce the size of the transistor RF, then we can also reduce the supply voltage by S. So if the size becomes 1 over S, then supply voltage also becomes 1 over S. So it is true that so actually in the old generation CPU, the supply voltage was 5 volt. And then recently the supply voltage of the recent CPU is just 1 volt, and then actually it's just around 1 volt. Okay, so if the transistor size is reduced, we can also reduce the supply voltage. If the supply voltage is reduced, then it's very good, right? Because the dynamic power is the proportion of the square of supply voltage. And then we can increase the frequency, the speed of device, right? So actually, the speed of device is determined by the electric charge that crossed up this transistor channel. Okay, so actually, in order to understand the spectrum, then you need to learn about the semiconductor devices. But you can understand it like this. So the speed of a transistor is determined by this time. The time that electric charge passes through the transistor channel. Just think like this. If the channel size is reduced, and then if the electric charge speed is the same, then it will take shorter time, right? Because channel is reduced. Then the transistor speed is determined by how long it takes when the electric charge passes through the transistor channel. Okay, so which means that we can increase the F by S. So for a single transistor device, the dynamic power is reduced to 1 over S squared. So which means if we reduce the channel width by S, so if the channel width becomes 1 over S, the dynamic power can be reduced to 1 over S squared for a single transistor. So another benefit is that the size of single transistor also reduced, which means that in the same area, we can include more transistors, right? Because the transistor size is reduced by 1 over S squared also, which means actually at the same for the same area, we can have S squared transistors. The power consumption of a single transistor is reduced to 1 over S squared, but in the same area, we can include the S squared of transistors. So, which means if we just multiply these two numbers, then it is 1. It's Dennard scaling. So, Dennard scaling means that if the semiconductor technology is advanced, and we can use smaller transistors, and which means that in the same area we can add more transistors. So which means that we can invest more hardware resources. And then if we can invest more hardware resources, then usually we can improve the performance of CPUs, right? If we invest more hardware resources, then we can increase the performance. But in the same area, the power consumption is the same because each one, it's not changing. So this is the Dennard scaling. So which means that if the semiconductor technology is advanced, the power density of the CPU is the same, but we can add more transistors. That's Dennard scaling says to us. Okay, it's very good, right? So which means if the transistor technology, if the semiconductor technology advances, then we can improve the performance of CPUs without any cost, right? Because the power is the same, but in the same area, the So this our chip will include more transistors. It's very good. It's very good news. If the data scaling is maintained. But it's not true recently. So this graph shows the size of the transistor. So which means this red line indicates represent the channel width of the transistor. So as you can see, the channel width is reduced. But the blue line represents the power density. So which means that the power consumption per unit area, right? So if the data scaling continues, then this blue line should be the same, because data scaling represents that if the semiconductor technology is advanced, which means that if the size of the transistor is reduced, the power density is maintained. But in reality, it's not true. As you can see, the power density is also increased. Why? There are many reasons, but actually, in this slide, we just mentioned the dynamic power consumption. And then if the transistor size is reduced, transistor consume more static power. The static power. So static power means that we assume that if the transistor is a perfect device, then if the transistor is turned off, then transistor does not consume any power. The baseline assumption is if a transistor is a perfect device, which means that actually even though the transistor is turned off, then transistor consumes also power. And then this power consumption is called static power consumption. So which means that even though the processor is off, the process does nothing. So but our processor also consumes power because of static power. This static power increases as the size of the transistor increases. That's the problem. Also, because of the threshold voltage, we cannot reduce supply voltage. So I said that the supply voltage of the CPU is reduced from 5 volt to the 1 volt. But recently, also this supply voltage is saturated. It's not easy. We cannot reduce the supply voltage of our recent processor. So, which means even though the CPU size is the same, the power density is increased, which means that even though CPU size is the same, because we can use the smaller transistors, but our CPU will consume more power, and that's the problem. I said the cost is also very critical because the purpose of the power consumption, besides the running cost and then the heat of the CPU. So if the power consumption is increased, then we also need to invest more money for cooling system, because our CPU just work at a certain range of temperature. If the temperature is very high, then our CPU will be broken. So running cost is also very critical because it's modern. Okay. So I switch to multiprocessor. And then because of this power limit, our CPU is CPU architecture is changed to the multiprocessor. Sorry, my writing is not good. And then what is multiprocessor? What is all multiprocessor? Actually, the multiprocessor means multi-core architecture. So if you read the specification of the Intel core architecture, like Intel i7 and i5 and the i3, then you can find that Intel i7 has 6 cores. i5 has it's not the exact number. I just example 4 cores and 2 cores. What does that mean? Actually, the core is the independent processor, which means that core can run an independent application. And then, if for example, i7 has 6 cores, actually 6 physical cores, so which means that i7 can run 6 applications, well, 6 threads simultaneously, concurrently. So, which means i7 can run 6 independent applications at the same time. So why do you use the multiprocessor? So what is the benefit of multiprocessor architecture? So what is the benefit of increasing number of cores? Latency? Right, throughput. Actually, the latency is the same, right? Because the core is the same. If the core performance is the same, and then I assume that, so I mentioned that only one thread or one application can run on this one core. And if the core is the same, which means that the latency, response time of this single thread or single application is the same. Because the core is the same, nothing changes. Nothing is changed. But if we increase the number of cores, then we can run different applications or different threads concurrently using many cores. So which means we can increase the amount of work done in unit time. Because there are more workers. And then if we invest more workers, then we can expect that more workers can do the more amount of task. Okay. Then why the architecture is changed to the multiprocessor? And then this graph shows the performance of uniprocessor, which means that the performance of a single core. So as you can see, the performance is increased. So just to mention, as you can see, this is the log scale y-axis. So it means that the performance is increased exponentially, right? It's 2% per year. It's amazing, right? So exponentially, the performance is increased by 50% per year, right? It's amazing. But recently, the performance of a uniprocessor with single core is saturated, right? There are many reasons, but the first reason is power consumption. So I said that in order to increase the performance of a single core, we need to increase the clock frequency. But it's not possible because of the power consumption. So we cannot increase the performance easily. Also because of the end of the Banner scaling, so it's actually the same area, the Banner scaling. Also, the CPU consumes more power. So we cannot increase the performance. But if we add more cores, then we can increase the throughput of our CPU chip. Okay. So we can increase the throughput. But problem is that we cannot increase the latency of a single thread application. And then in order to use the benefits of multi-core architecture, then which means that we need to write the parallel processing applications. Okay, so for example, it's a single application like so think about the internet browser, but in order to accelerate the performance of the internet browser needs to support the parallel processing, which means that internet browser needs to generate multiple threads, and then these multiple threads need to be executed simultaneously, not exploit multi-core architecture. So which means you need to develop the where is so we need to develop the parallel algorithm. Okay, we not to use the benefit of multi-core architecture. Also, another so avoid is the load balancing and then communication and then synchronization overhead. So think like this. So team project is assigned. So let us assume that the team project is assigned to you, and then you can include more members. Okay, but real life, so one team has 2 members, and then another team has 4 members. But in real life, can you observe the performance of this team B, the team A? The performance of team B is always higher than the performance of team A by twice. It doesn't happen in real life. So there are many reasons, because the first reason is that some tasks cannot be split into multiple tasks. So some tasks need the serial execution. So another problem is communication, and then a communication issue. So even though many workers work together, and because of the communication issue, then we cannot get the performance proportional to the number of workers in real life. And it's actually the same to the computer system. So even though there are many cores, then in order to complete our task, the single task, then these cores need to communicate each other. So which means that some result of the one core need to be delivered to the other cores. Okay, and then these results can be used by other cores. And then because of this communication and synchronization issue, then performance is not proportional to the number of cores. Then this issue is called the scalable issue, scalability. So we cannot get scalability with the multi-core architecture. This is another issue of the multi-core architecture. Okay, so in this class, so I explained, we discussed about the consumption of the processor, the computer system, and then we learned about the NAR scaling. Okay, then we learned why the power density is the same with the NAR scaling. But recently, the NAR scaling is not applied, which means that the NAR scaling already ends. The power density is increased. And because of the power issue, then we use the multi-core architecture recently. Okay. Okay, so next time we will learn about some benchmarks. Then so we will learn about the Moore's law. Okay. Okay, so I will stop here. Any questions? Okay. Thank you for attention. See you in the next class. 감사합니다.